to be finishing taking notes from video today. So everybody should have their notes already out. Everybody should be on the section page 2. We're going to finish the evidence of the Big Bang. Now, I'm not sure where all the classes are at, so I'm going to start maybe back in time a little bit. We have known that as the universe has gotten older, that this original heat energy that must have been left over from the Big Bang, at least theorized by scientists, had to still exist. And their theory was that it had stretched with space. As space expanded out in all directions, that this radiation energy, this maybe very violent gamma radiation, had stretched over time to become either microwave waves or radio waves. So the evidence of the Big Bang, again, I think most of you actually have this down, but I'm gonna go through it just really quickly to make sure everybody has it. So we talked about these spectral lines. Let me go back real quick. And that, let's say this chemical, whatever this chemical is, if this object is in motion, if this is where these spectral lines should be, then if it's in motion, all of them will be shifted. All of these lines the same distance apart, but they'll be shifted into a different direction. Now, if that object is moving away from us, all of those spectral lines will have shifted slightly towards the red end of the rainbow. So here you can see this green is now more yellow-green. This blue is now more of a teal color or a light blue. All of these lines are shifting towards that red end of the rainbow. Remember, that's called redshift. Now, if it was all shifted downward and they were all shifted towards the blue end of the rainbow, we would call that blue shift, and that would mean that the galaxy or star or whatever this object is would be coming at us. Now, when Hubble looked out in space, here this is a photograph of the night sky about an inch, if you were standing and measuring from the ground surface, is an image here from outer space. Now what he looked at and what he saw, and these are all galaxies, not one of these is a star in our own galaxy, is nearly every single galaxy was redshifted. Now remember, not all of these are red. They're redshifted, but that doesn't mean they're the color red. So here we've got yellow galaxies, we've got some that are just white, we've got some here, that are orange. And then if you can see in the photograph, the really far distance one, this tiny little blip of light, all of these are actually red. So what he found is there was a direct proportional relationship between the distance of galaxy and their redshift. Now remember, the redshift means their speed. How much redshifted they are tells you how fast they're going. So this galaxy here that's just yellowish isn't moving away from us as fast as this orange galaxy. And this red galaxy, these red blips that maybe you can't even see, but I can see on my computer, are going so fast. And they are the furthest galaxies from us. So there's a direct relationship between speed and distance away from us. And he concluded, since most of the galaxies, a huge amount of galaxies, are red-shifted instead of blue-shifted, that the universe was in fact spreading out. It was expanding. Now the things that are further away are fastest because all of the space between the galaxies is stretching out. It's all stretching out sort of at the same rate, but things that are twice as far away from us, there's more stretching distance between us and that galaxy than ones that are closer to us. Alright, so let's go ahead and write that evidence down. Galaxies are redshifted when we look out, and the further the galaxy is, the more redshifted that galaxy becomes. This indicates the universe is actually expanding and spreading out. So you may be able to say, okay, so maybe the Big Bang Theory isn't exactly interpreted correctly. Okay, maybe we wouldn't be able to say that. Maybe other scientists that study it and know a lot of information about it could say that. But you can't refute this. This is evidence. So remember that inferences are assumptions made based on facts, but facts are statements of truth that cannot be argued. So this is an example here of fact that cannot be argued. It is a fact that galaxies out in the universe are all expanding, or not, they're expanding, that they are moving away from us, and that the the distance almost determines perfectly the speed at which they're going. If they're going twice as far away from us, they're going twice as fast. It's actually not double the relationship. It's more like a triple thing, but it doesn't matter. It doesn't matter. Oh, sorry. If you need more time to write that down, hit pause, tell everyone's done writing, and then I'll move on. All right, the second evidence we have is that heat radiation that the Big Bang predicted, that the space is spreading out, so the radiation's to spread out. This is what they found. This is number 2, evidence number 2. It's called cosmic microwave background radiation, also known as CMB for cosmic microwave background radiation. This is the leftover heat signature from the Big Bang. Now write it down and then we'll explain it. And it's detected in every section of the night sky. So it's basically the constant radiation that's emitting from every inch in space, and it isn't coming from like a distinct star or galaxy, but instead is spread over the entire sky. So this globe thing that I have here is not of a planet, or is not of the Earth, but it's basically our vision of the sky, sort of represented in 2D, which is super weird. But imagine that we have a map of the night sky. And this is what it looks like. Every blip in color on here is radiation. Here we have less radiation where it's dark, and here we have more radiation where it's lighter. Now these lighter points may be places where stars are shining light at us and we're getting microwave radiation shining right at us. But basically we see a covering of the entire night sky. There's nowhere where we point our instruments into the night sky where we can't see this radiation. So this was discovered by a couple of scientists. Names were Areno Penzias, I don't know how to say his name, and then the other guy is Robert Wilson here in the front. Behind them is their antenna. This is receiving the microwave background radiation that they detected. Looks like a giant metal cornucopia. But what I find interesting about these two is they were looking in the night sky and they were trying to create this device that could analyze distant stars and the radiation that was coming off of those stars. So to start, they wanted to zero out their device, point it to a night sky where they would not be getting any star radiation from, and just make sure we started at 0 so they could, any measurements they made would definitely be coming from the stars. What they found was what they called noise that was just coming from everywhere. So they thought, okay, there's something wrong with the machine. Maybe it's got bird droppings in it or something. They went out, they literally climbed in the machine, they scrubbed it clean, and then they came back to the computer, and it was still receiving this noise or static. And they couldn't figure out what it was. So they went to some of their friends in the physics departments and said, do you know what's going on? How are we getting this noise information? Why can't we zero our machine and get it started? And what I think is interesting is their physicist friends were studying the Big Bang by coincidence. And they said, oh my gosh, you actually found the leftover heat radiation that we've been looking for. You found the heat signature. I mean, it's not heat anymore. It's microwave background radiation. And they thought it was really pretty amazing. So these two, Penzias and Wilson, had no idea what they had discovered. Not one clue in the world. And they had to be told by their physicist friend what they had found. But what's interesting is they actually ended up getting an award, the Nobel Prize for Physics that year in science, for this massive discovery that helped provide evidence for the Big Bang. And with that comes a reward of $1 million as well, which is kind of cool. But I think it's funny they got the $1 million even though they had no idea what they had stumbled upon. So our third evidence that we're going to need to know for the exam is the abundance of elements that we see. In the beginning, we had hydrogen, helium, a little bit of lithium, maybe a little beryllium. But for the most part, like 76% of the entire universe was hydrogen, and the rest of it, almost completely all of it, was helium. That's all we had. So this evidence, the fact that we have all these other elements, we have things like plutonium and gold and phosphorus and sulfur and oxygen and more lithium and sodium, all of those other elements were created over time. So as stars began to form, they formed more and more of these elements. So this evidence is more of showing that the universe is changing or evolving over time because we have this large abundance of elements. So write this down. Abundance of elements. In the beginning, there was only hydrogen and helium. And as time has allowed for more elements to be created in stars. So it had to be a long period of time for this to have happened. I mean, you can't make a planet like ours with all of the elements that it has without first going through many of these processes. Now, we will be talking more about stars later on in the class, so if you're like, well, this is the only thing we know about stars, that's pretty crappy knowledge, but our next section is on star formation and death. Pause the video if you need more time to write this down. Alright, so we don't need to write this down. You can actually scribble this out of your notes, so nobody needs to write any of this down. There were two main ideas of how the universe might end. One of them was called the Big Crunch. We definitely have debunked this. We know that this cannot happen due to the mathematics that we've done and factoring we've done and the new discoveries we have discovered with dark energy and dark matter. We know we are not talking about those in this class. I'm sorry. But basically it's the understanding, or the idea, not understanding. It's the idea that gravity will eventually take everything hold. So everything is propelling apart, right? Everything's expanding. Everything's moving away from everything else. And eventually gravity would slow the entire universe down and pull things back in. And eventually everything would get eaten into a massive, gigantic black hole. And then the universe would start again. But because we have discovered dark energy, not only do we know that the universe is expanding, but it seems to be speeding up. And it seems to be speeding up because of this dark energy. Now, we have dark energy and dark matter. We call it dark, not because it's black, because we can't see it. We can't detect it. We can detect its effects on other objects that we can see, but we actually cannot see dark energy or dark matter. We can just see the effects that it has on matter and energy that surrounds it or is near it. So again, we call it dark, not because it's dark, because it's mysterious. So the second idea of how the universe might end is called the Big Cool, where it's the idea that everything is spreading and propelling out so rapidly that eventually things will be so spread out that we won't be able to collect enough hydrogen to form stars and start nuclear fusion processes, and eventually the stars, one by one in the universe, will start going out, and everything will become dark and cold and lifeless. But, I mean, hey, long after we die. I mean, this is said to be maybe at the earliest billions and billions and billions and billions of years in the future. Not even a good projection on when that would happen. And by that time, our entire planet will be destroyed by our own star when it dies. So, good thoughts there. All right, that's all the notes that we need. You are now going to do a review worksheet that primarily you can completely do with your notes, except for the backside. You're going to actually have to think and evaluate stuff on your backside. The backside of the paper actually has some questions that are very similar to the test to help you. So make sure you're doing those right. And then you're going to review for the exam. Make sure you're ready for the exam. The exam is next time. Happy studying.